Hello, Paolo and Luca. Welcome to our new video podcast on soft magnetic composite. Well, would you like to start introducing yourself, Paolo?
Right. Hi, Peter. Thanks for your invitation. My name is Paolo Bolognesi, and I am with the University of Pisa, Department of Energy Systems, Territory and Construction Engineering. I work in the field of electric machines, power electronics, and electrical drives. I've been involved in these topics since many years now. Both from the point of view of teaching and also from the point of view of research, and also applied research in collaboration with companies, in this case with Sintex. So thanks for your invitation. Well, I'm very much interested in new materials and new topologies of machines. So this talk, this discussion we are going to have about SMC for me is actually very interesting.
Thank you. And also welcome to you, Luca.
Hi, Peter. Thanks for the invitation. And myself, I relate to what Paolo said. I work in the same department. I've been working in the UK for many years, and then after a while, I came back here in Italy, working at the university, focusing on electrical machines mainly, and manufacturing and multi-physics design of electrical machine for transportation, for renewable energy, and for industry application.
Yeah, thank you. And I myself, I'm Peter Kjeldsteen. I'm working with innovation and marketing at Sintex in Denmark, where we are producing soft magnetic composite materials and would like to find application and investigate new areas for where SMC can be used. There we are. The agenda for today would be introduction, who are we, then an introduction to what is SMC, what are typical properties for SMC, then a discussion on the supply chain in the electrical motor market, and a discussion on SMC as a stator material. Does it work? What benefits can it give? And so on. But first, a short introduction to what is SMC. SMC is a powder-based material. Every single powder particle is isolated. So it's like laminated sheet that is isolated on each side. But here, every particle is isolated, and typical particle size is around 100 micron. Those particles are then compacted into a part that is called a green part, and the green part is afterwards heat treated to have the final properties both mechanically and magnetically. Afterwards, it can also be surface coated to have corrosion protection and so on. Typical properties of SMC, if we look at down here, the saturation level, we can typically reach the same saturation levels as you can with iron. So around 2 Tesla is reachable. Then when we go into motors or frequency applications, we see some loss curves as a function of frequency. And if we look at the DC level where we have no frequency, typical SMC has a higher loss because the heat treatment that we make after compaction does not fully anneal. So we still have some deformation, hardening deformation left over in the part. If we went to fully annealing, we would also initiate a sintering, and a sintering would shortcut the particles and destroy the isolation. So therefore, we have in SMC a trade-off. How high can you go in temperature to have a better annealing, but not too high to destroy the isolation layer. So therefore, we typically see a higher loss at low frequency compared to other materials. But when frequency goes up, we can also see that the losses, they are not growing that much. So therefore, we often claim that SMC is an advantage material when we have a higher frequency in our machines. Mhm. Do you have any comments to the manufacturing process and the properties you see here?
Well, let's say it's very interesting from one point of view to see how effective it can be, the insulation that you mentioned. Indeed, looking at the properties on the left for material H1, we can see that as in the graph, we have reported the losses per cycle. Indeed, so the energy lost in each cycle, it's practically constant with frequency, at least in the range that is analyzed here, which means that actually the insulation between the particles is very much effective, because in practice we only see hysteresis losses there. And when you go for a different material, the M7, then you can see lower hysteresis losses, which are the ones that you can see at the beginning of the scale, basically, which sum up with, let's say, increasing eddy current losses. And there is exactly the effect of the process you described. So you have a somewhat less effective insulation between the particles. So you have increasing eddy currents losses, but you got better annealing, which means lower hysteresis losses. So it's a matter of a trade-off. So depending on the operational frequency that you are going to envision in your application, you can find more interesting going for, let's say, towards a less insulated material, but with lower hysteresis losses, like the M7, rather than for a material which is better insulated, but with higher hysteresis losses, like the H1. Only one comment about the laminations. Typically, for higher frequency, you would go for thinner laminations. So here you have the losses for 0.5 and 0.65, but indeed those thickness values would be not so much suited for applications going above, let's say, 1 kilohertz or so. Normally you would go for 0.35 or something like that. And in such case, you'd have lower losses, obviously, for eddy currents, because the thinner is the lamination, and the lower you get in terms of losses for eddy currents for the same level of flux density and so on.
Yeah, so typical thickness is 0.35 in industrial applications today.
Indeed.
Yeah, in automotive, they go even thinner, don't they?
It depends on just on the frequency and on the target that you have in terms of losses. If you go very, very thin, you can even have applications in which you go below 0.1, but those are indeed tapes rather than laminations, because they become obviously very much flexible. Then you need something to put them together and to keep them in the right shape, because otherwise you will have something just resembling paper sheets or something like that.
Okay. Yeah.
Yes. And for the other properties, I would say, it's interesting to see that we can come to flux density values which are pretty high, but on the other hand, you need a pretty high value of field strength also to achieve that level of flux density. So you have to keep this into account in the design of your machine. Typically, the permeability, and we can see that very well. I see in that diagram. It's very interesting. As you can see, that the differential permeability actually goes down pretty quickly. And so when you go above, let's say, 1.5 and you approach 2 as a level of flux density, 2 Teslas, you can see a level of permeability going down very quickly. and you are basically in the order of 100 or less, tending to maybe, I don't know, 10 or maybe even less. And obviously this has to be kept into account very carefully when you design the machine. So let's say these materials are very interesting from some point of view, but on the other hand, they do require a design process which is more suited, more tailored for the properties. And so you need to understand very well how the machine operates, and even to envision how to exploit at best the properties of these materials. I'd like to mention about this the 3D capability. In my opinion, it's a very powerful lever. So in the case you are able to envision a structure of the machine which is capable to let's say to pivot on that in such a way to exploit it, actually that could be very much interesting, because you could go towards machines which cannot be done with laminations. So then they cannot be made using laminations. So it's a completely new field of applications that you can envision.
I'm jumping to the next slide, because you just said this with design possibilities. We have made a simulation on a new design, and this is not very complex design compared to what you can do with SMC topologies. But if we look at the motor design at the bottom, this is a standard laminated motor where the winding of copper has an overhang. But on the upper, we have designed it with SMC material, and there we have reduced the height of the bridge in the teeth, enabling us to make the winding within the height of the stator itself. So there's no overhang, there's no end windings. In this case, we were able to reduce the amount of winding with 30%. And that itself, when it's copper, it's a lot of money, but it's also a quite high reduction in losses, because in many motors, the majority of losses are copper losses. It's not iron losses. So just by reducing the length of copper with 30%, you can reduce the losses with 30%, but you can also reduce weight a lot. And in this case, we try to simulate on the weight, and you can see in the table when going from copper to copper, just changing the design, we can reduce the weight from 412 to 310 grams for the stator. If we change that to aluminium for the winding, for reducing weight even further, the weight of the SMC component combined with aluminium could be reduced even further down to 250 grams.